All right, so this is P3, functions and their graphs. So referring back to last lesson, the kickoff there, what are the different types of slope? Your different types are positive, negative, no slope, and undefined. So positive is when we go from left to right, we're working up. Negative, as we go left and right, we're working down. No slope, we're horizontal. Undefined, it's a vertical. So, the official definition of a function, let x and y be sets of real numbers. A real valued function f on a real variable x from x to y is a correspondence that assigns each number x in x to exactly one number in y in y. One number y in y. X is the independent variable, y is the dependent variable. So what that's really saying is, with a function, we're going to be able to make a relation. So we're going to pair up numbers in our x's to our numbers in our y's. So that they're joined together, they're tied together, they have that relation. X is going to be an independent variable, so that's usually the number that we're plugging into the equation. And then y is our dependent, that's how it ties, that's where it's coming from. So think a function, we have a relationship between two things, our x's and our y's. So think ordered pairs. The domain of it is going to be all of the set of x's. So any x that we could use is going to be our domain. Y then is the image of x under f and is denoted f of x, which is called the value at f at x. So think y is going to be the value that our function is going to equal in the end. The range is going to be all of the y's. So what values are we going to get out of this equation? And again, we use f of x a lot of times. That's just to name our equation that we're working with. A lot of times you'll see it as f of x or h of x or g of x are more of the more common ones. But all it's really doing is when we have multiple equations going on, it's allowing us to name which equation we're talking about. So we don't just have a whole bunch of y equals. Now there are different forms of functions. When the x and y are on the same side, that's an implicit form. So think just about looking at this, it's hard to tell what y is. Or what our function, whether it is a function or not. Explicit form is when we have it in the y equals form. So this looks like our general equation that we're used to working with. You know, all we gotta do is put it in our x, and we can work it out, and we can get what y is. It's very straightforward. Here we gotta do a little more work to it to get to solve for our variable there. And then function notation. So this is how we'll write it. Like I said, you'll use f of x. That's just a way to identify which equation we were dealing with. With functions, we can then go ahead and put values in for x. So like here, if we have f of -2, that's saying, okay, our f function that we're dealing with, what is the value when we put -2 in for x? So we would go through here and do f of -2. So 2 parentheses -2 squared minus 4 times -2 plus 1. So we replace every x with that -2. So what's in parentheses here? So -2 squared would be 4. 4 times 2 would be 8. 4 times -2 would be minus a -8. So in other words, plus 8. And then our plus 1, we end up with 17 then. So just keep in mind, whatever's in here, every x in that equation is going to be replaced by. This here you would have remembered from, well, you might have remembered from advanced math. Although it would have looked like this, f of x plus h minus f of x all over h. It's the difference quotient, so it's just changed a little bit to the change of x's that we're going to use for calculus. So it's same idea, just a little different looking. So what we're going to do here is first we're going to take our function, we're going to replace every x with an x plus h. So if this here was our function, here our x squared plus 7, we would now have x plus change of x squared plus 7. So the x part, we sub in x plus change of x. So it was squared, so we square the whole thing, and then plus 7. Now, if I square this out, x plus change of x times x plus change of x. So first, x and x will make x squared. outsides, x times change of x would be a plus x change of x. Insides will give us another x plus change of x. And then last would be a change of x squared. So when we write this, we're really going to have x squared plus 2x change of x, because I'm going to put these middle two together, and then plus change of x squared plus 7. So I just FOIL this out, replaced it with that. So that's this first part, this f of x plus change of x. The next part is they want us to subtract the original function. So if this is our original function, we're going to subtract out the x squared plus 7. Now I'm going to put the whole thing in parentheses because the whole thing is getting subtracted, so we got to distribute this negative. And that's all over the change of x. So if we do distribute this negative, that would make this negative, that would make this negative. So now we can start canceling stuff out. We have an x squared and a negative x squared, negative 7 and a plus 7. So after this first round of cancellation, the only stuff that's left should have a change of x in it. So we have a 2x change of x that's left here and a change of x squared. And then it's still all over change of x. So at this point, every term should have a change of x. So now we can reduce it. This top here has a change of x, and then 2 of them in this term. So we're going to get rid of 1. And those will cancel with the change of x on the bottom. So our final answer, 2x plus change of x. And that'll be the final answer for that one. Sometimes the domain is going to be given with the function, and all that's going to do is it wants to reduce what's possible for the domain, because there's probably going to be areas where either you want to focus on, or it's just areas that'll cause us problems. So like this one here, we're going to restrict the domain. That's what this part here is doing. From 4 is less than or equal to x to less than or equal to 5. So from 4 up to 5, any of those x's we can use, and that's what we're going to restrict it to. Now, part of this is if we put 2 or negative 2 in, 2 squared would be 4, 4 minus 4 is 0 on the bottom, which makes it undefined. Same thing with negative 2. So those would be problem ones. So we're going to exclude that, otherwise we're going to run into problems. So if we don't give the domain, then we would go through and go, okay, well, our domain actually is going to be everything except these two things that cause problems. So they're still going to restrict it a little bit. Now, when it comes to finding domain and range of a piecewise function, you got to look at it a little differently. It's not so easy to just look at and know, although the domain it will be. Domain, you're going to look right here at this stuff. So what we're looking for, all of these x's is going to be covered based off of our conditions. Now again, piecewise function is for a certain amount of x's, we're going to use this equation. For certain x's, we'll use this equation. It gives you an either or type of a thing. We can use this equation or this equation based off of what x is. So when we're looking at these x's, this first one says, okay, we want x that's less than 1. So everything less than 1 is going to be covered by the first one. The second one, x is greater than or equal to 1. So 1 is included and everything bigger. So in this case, everything's going to be included. So we're going to say all reals. Or you might see it as negative infinity to infinity. Either way works. And we really, I guess, don't need parentheses around all reals. So that would be the domain. As far as range, range now is where it gets a little more complicated with this stuff. So the first thing you're going to look at is what number are we breaking your break point there. So where is it splitting between the two equations? Well, we're splitting at 1. So we're going to look at both of them when x is 1. So if we put 1 into the top one, 1 minus 1 is 0. So we get 0 out. When we look at the bottom one here, x minus 1, so if we put 1 in for x, so 1 minus 1 is 0, square root of 0 is still 0. So we get 0 either way. From there, though, we're going to look at what about a value inside here. So right now, they're both 0, so they're going to be at the same spot. There's not going to be a jump. There's not going to be a gap. But from here, we need to see where are we going with our graph. So on this top part, we want an x less than 1. So what's an x less than 1? Let's do 0. So if we put 0 in here for x, that's going to fit this criteria. And 1 minus 0 would be 1. So that means we're going to get bigger than where we started. So we're going to be going up from here. Now we need to look at the other side. Where is it going to be going? So we need an x that's greater than or equal to 1. We already did 1, so we want to go bigger. So we're going to do an x of 2. So if we put 2 in here, 2 minus 1 is 1. Square root of 1 is still 1. So again, this one's going to be increasing as well. It's going to be getting bigger. So in this case, we're going to start at 0, and we're going to go up to infinity because we're going to cover all these. So our range here is going to be a bracket because 1's included, so we could get 0. And it's going to go to infinity. So that's how that's going to be. Now, if we would have gone through and, okay, this one's going up and this one's going down, that's going to cover them all, then it could have been all reals as well. There are also situations where maybe these aren't the same number. Then you have to look at, okay, are we going to overlap? Or are we going to have a gap? And so that might change our range. So it's all going to be based off of what's going on at this breakpoint. And then from that breakpoint, what's our graph doing? Is how you're going to find those. Now, we can get further into functions with, well, a function is 1 to 1 if each value in the y, the range, corresponds to exactly one value of the domain. So the x's aren't repeating, the y's aren't repeating, is when it's 1 to 1. There's only one x for every one y. Now, for it to be a function in general, the x's can't repeat. So if we put in an x, we're only going to get one y out. Now that y could repeat, that could go with multiple x's. So maybe at 2 it's a 3, and at 4 it's a 3 for a y. But we can't have, when x is 2, we get, well, y could be 3 or 4. We can't have multiple x or multiple y's. Only that one y for that x. So it's considered on 2 if the entire range is used, if you think of it that way. So all the y values that are possible are going to be used. So, like for example, y equals 2x isn't on 2. Well, I guess it could be. I gotta think of a better example. But think of one where it's gonna end up skipping certain values. So that one wouldn't be on 2. So like y equals x squared could be considered not on 2 because you're only gonna include, from 0 and above. We're not gonna include all the y's in that sort of case. Vertical line test is something that we use to check to see if it's a function. So if we lay our pencil down, say for example, and if we drag it across our graph, if it touches our graph more than in one spot as we go across, so like say if it touches here and it touches up here, if it touches in 2 spots as we drag it across, then it's not going to be a function. It can only touch our pencil once as we go across the graph. So that's your vertical line test. Now, there are basic transformations that are going to go on with graphs. So this was stuff we talked about in advanced math, so this should be review. But if it's not, it's okay. We'll go through it here. So if our original graph is y equals f of x, so whatever our function is, if this is our original graph, if we subtract c here on the inside, that's going to be a horizontal shift. So inside the function with the x, if that changes, it's going to move it left and right. Now, if it's negative, it goes to the right. If it's positive, it's going to go to the left. It always goes opposite on the inside of what you think. If we subtract on the outside, it's going to go where we want. So negative on the outside, go down. Positive on the outside, go up. So if we take our function, whatever it is, and we just add to it or subtract to it, we're going to move it up and down. To make it wider, we're going to be between 0 and 1. We're going to times by that x on the inside. So think, if this is smaller, that's going to make our graph wider. If this is bigger than 1 and we times by it, that's going to make it skinnier. So wider, skinnier, again, inside affects horizontally, and it's always opposite of what you think. If we times the whole function on the outside, then it's going to go where we think. So bigger than 1, it's going to get taller. Between 0 and 1, it's going to get smaller. Now, we don't include the negatives because the negative is going to have its own effect here. So a negative on the outside means it's going to reflect across the x-axis. So we're going to take it and we're going to flip it over the x. So if it's down, it'll flip up. If it's up, it'll flip down. If it's negative on the inside, if we add that negative in, that's going to reflect about the y-axis. So it's going to take it on the right side, flip it over to the left, or the left, flip it to the right. And then if it's both, it'll flip around the origin. So we'll take it and it'll rotate 180 degrees. Okay. The three main types of elementary functions are algebraic functions, which is what we usually run into with, so polynomials, radicals, radials, rationals, all those are involved in algebraic expressions. Trigonometric functions, your sine, cosine, tangent, those functions, we kind of hit a little bit in advanced math. We'll work with them a little more. And then exponential and logarithmic functions, again, we cover those in advanced math as well. So these are the three types of elementary functions, so the main functions that we're going to be working with. We focus on the polynomial function here. So polynomial functions are going to be the most common type of function, and we have it in that form of f of x equals a sub n x to the n plus a sub n minus 1 x to the n on down. So really what that's saying is we're going to have our biggest exponent, then our next biggest exponent, and work our way down to where we don't have any exponent for an x, for our variable. And that a is just the coefficient that's in front. So a sub n is going to be your lead coefficient. That's going to be the very biggest exponent on the variable, whatever number's in front of it, and is that degree of the polynomial. So if our biggest one is, say, to the third, would be a third degree polynomial. If our biggest x to the n is to the seventh, it would be a seventh degree polynomial. A sub 0 is going to be the constant term. Notice how there's no x with it, so it can't change. That's going to stay constant. Now, this will all include constant functions, linear functions, quadratic functions, cubic functions, all those type of things. So constant functions when we don't have an x, linears when we just have an x, quadratic x squared, cubic x to the third. So with that, we can use leading coefficient test to determine what the behavior of our graph is going to do on the ends. So if we start here, if we know it's an even degree polynomial, so a squared to the fourth, to the sixth, whatever, both sides are going to go the same way. Now, if that leading coefficient's positive, so that leading number with that x is positive, they're both going to be up. If it was negative, then they're both going to be down. If it's an odd exponent, so if that biggest x is, say, to the third or to the fifth, to the seventh, one's going to go up, one's going to go down. If that leading coefficient's positive, the left is down, the right is up. And if it's negative, the left is up and the right is down. So we can use this looking at the polynomial and know, okay, this is what the ends of our graph are going to do. As far as rational functions go, we can make fractions with polynomials. So think polynomials over a polynomial here is what's going on. However, we just can't have the bottom be 0 because, again, that's bad. We don't want to divide by 0. And keep in mind, functions can be added, subtracted, multiplied, and divided, just like variables and anything else in math. So we can take a function, we can add it to another one, we can subtract it, multiply it, divide it, all that stuff. All right, so if we have these two functions, we have f of x is 2x minus 3, g of x is going to be x squared plus 1. So if we add them together, we're going to add like terms. So x squared, this one's got it, this one don't. So we're only going to have the 1x squared. We have a 2x, this one doesn't have anything, so plus 2x. And I have 1 plus a negative 3, which would be a minus 2. So add like terms when you're doing it. Subtraction. So f minus g, we're going to take the f function and subtract it, or subtract the g function from it. So in this case, this doesn't have an x squared, so we're going to minus x squared from it. We have 2x, and we don't have an x squared here, so we're not going to subtract anything there, so it's just plus 2x. Now we have negative 3 minus 1, and get a minus 4 for that equation. Times them. So 2x minus 3 times x squared plus 1. We're still binomials, so we're still going to FOIL. So 2x and x would make a 2x to the third. Last, 2x plus 1 would be a plus 2x. Insides would be a minus 3x squared. And last, -3 times 1 would be a -3. So if we write this in descending order, we'd have 2x to the third minus 3x squared plus 2x minus 3, because that's generally how we do it, descending order. So the biggest exponent, and the next smallest, and the next smallest, and on down. When it comes to dividing, 2x minus 3 over x squared plus 1, you'd look at factors. We can't factor the bottom out, so no factors match up. So this is as far as you can generally take it. Composite functions. So we can take functions and put them inside of other functions. So like f of g here, we would take the g function and replace every x in the f function with that equation. So you might also see it as f parentheses g of x. So like I said, it's composite of f with g, so all of g goes in for f. So if we start with f of g of x. So we're going to take the f function here and replace it every x with a g function. So 2, that x becomes cosine of x minus 3, and that's really as much as we can do with it. So that's it. If we do it the other way, now we're going to take the f function, put in for x of this one. So cosine of 2x minus 3, and that one's done as well. So lastly, determining even and odd. F of x is even if negative x goes in there and we get the exact same back out. It's going to be odd if we put a negative x and the entire thing is different. So a lot of times you will look at these exponents, since this is technically the first. If those are odd, it's going to switch the sign, and so this one would change and this one change, which makes this one odd. If they're both even, it won't change the sign, so it would make it the exact same, and so then it would have been even. But because they're odd, we're going to be odd too. Now, where it's different is with cosine. We have, let's see here. So sine matches up with cosecant. Cosine matches up with secant, and cotangent, or tangent, tan, matches up with cotangent. So this goes back to advanced math when we were doing trig functions. These here are going to be even. The rest are odd. So cosine and secant are the only two that won't change when you put a negative x in. One is a constant, so it's not going to change at all. And cosine being even means this is going to be an even function. Okay. And that's it. That's it for this lesson. Let me know if you have any questions. You can always send me a message on Google Classroom or email me, or you can pan me. Let me know. Bye.